This is the lecture for Module 7 of Unit 5. In this module we discuss salts of polyprotic acids and acid salts. Okay. Carbonic acid has pKa1 is around 6 and pKa2 of a bit more than 10. Find the pH of a 0.15 molar K2CO3 solution and find concentrations of HCO3 and H2CO3. Right, we know Ka1 and Ka2 for carbonic acid, but here we have carbonate, which species arise after 2 successive deprotonations of carbonic acid. As the conjugate base of a conjugate base, you may expect carbonate solutions to be acidic. So if carbonate acts as a base, we're concerned with 2 reactions. Carbonate itself can react with water to remove a proton and make a hydroxide. Kb for that will be quite high, 2.1 times 10 to the negative 4, found by dividing Kw by Ka2. Note Ka for bicarbonate is used because we need to use Ka for the conjugate acid. We might then consider an additional hydroxide contribution. Bicarbonate and water reacts to produce hydroxide on carbonic acid. However, Kb for this is Kw divided by Ka1. Ka for this acid, the conjugate acid. And this produces 2.2 times 10 to the negative 8. Right. Kb1 we note is much larger than Kb2, so we can assume essentially all the hydroxide comes from the first reaction. A nice table, not showing change here, just showing initial and equilibrium, shows our carbonate concentration is 0.15, no hydroxide, no carbonate. In other words, we're looking at reaction 1 now, from a standpoint of the 0.15 molar carbonate. That will reduce to 0.15 minus X. We'll treat that as 0.15. Bicarbonate and hydroxide concentrations are X. Solution is X is 5.6 times 10 to the minus 3. Now remember, this is our first approximation as to the hydroxide concentration. 5.6 times 10 to the negative 3 is pretty close to 0.15, so we can address this with successive guesses. First guess is 5.6 times 10 to the negative 3. 0.15 minus 5.6 times 10 to the negative 3 is 0.14. So we'll take a second guess. We get X is 5.4 times 10 to the negative 3. .15 minus X is still 0.14. We'll call X 5.4 times 10 to the negative 3. We get a pOH of 2.27 and a pH of 11.73 is predicted for this solution. Acid salts are species in which it may not be clear whether or not the solution will be acidic or basic. Now these can arise from partial neutralizations. So bicarbonate, which we might expect could protonate to form carbonic acid or deprotonate to form carbonate. Bisulfite, which again could protonate to form the acid or deprotonate to form sulfite. These have varying acidic basic properties. So for example, HSO4 is acidic. the predominant reaction, well, essentially it reacts in water to make H plus and sulfates. So a solution of sodium bisulfate would be acidic, and bicarbonate is basic. Bicarbonate will react to form carbonic acid and a hydroxide ion in water. In general, an acid salt, one of these anions of an acid salt, can be predicted to be acidic or basic by examining Ka versus Kb. If Ka and Kb are not close, pH problems can often then be solved accordingly. For example, we know that this is the conjugate bisulfate is the conjugate base of a strong acid. In other words, H2SO4 deprotonates completely into bisulfate. If Ka for H2SO4 is essentially infinite, we expect Kb for bisulfate to be 0. In other words, you can take Ka for a solution of NaHSO4. We'll take Ka for the bisulfate and determine the pH of a sodium bisulfate solution from an ice table. We'll look at another type of example of this later in this lecture. Let's look at an example of how we determine the acidity or basicity of a bicarbonate solution. Bicarbonate has a pKa1, or carbonic acid has pK1 of 6.35 and pKa2 of 10.33. Okay, pKa for the bicarbonate is 10.33. In other words, its Ka is 4.68 times 10 to the negative 11. To find pKb, we can take 14 minus 6.35 is 7.65. And take anti-log of negative 7.65, we get 2.24 times 10 to the minus 8. Equivalently, Ka is 4.4 times 10 to the negative 7. So Kb for the conjugate base is KWKa, 1 times 10 to the negative 14 over 4.4 times 10 to the negative 7. Or 2.24 times 10 to the negative 8. What we have illustrated here is two ways to determine the Kb of bicarbonate. Notice that you must use the pKa or Ka of the conjugate acid, H2CO3, to find the Kb. Now Kb is greater than Ka in this case. 2.24 times 10 to the negative 8 over 4.68 times 10 to the negative 11. So we predict a basic solution, and bicarbonate solutions are a well-known base used to neutralize stomach acid, for example. Let's consider another example, sulfurous acid, pKa1 1.85, pKa2 7.21. So we may wonder about the acidity or basicity of a bisulfite solution. Ka for bisulfite is pKa2, the second dissociation Ka, so that's 7.21, and the corresponding Ka is 6.2 times 10 to the negative 8. Kb is Kw over Ka, where Ka is conjugate acid. Ka for the conjugate acid is 10 to the negative 1.85, or 0.014. We find Kb, 1.01 times 10 to the negative 14 over 0.014 is 7.2 times 10 to the negative 13. Alright, here the Ka is bigger than the Kb, so the salt is acidic. Sometimes, well, as we discussed in the case of bisulfate, it is possible to attempt a quantitative estimate of the pH of an acid salt. We'll consider a sodium hydrogen phosphate solution, Na2HPO4, and estimate the pH of a 1 molar solution accordingly. Remember, the sodiums are spectator ions. So the question is hydrogen sulfate an acid or a base? Ka for this is Ka3 for phosphoric acid, 4.5 times 10 to the negative 13 is to be found in a table. For Kb, we use Kw over Ka, where we take Ka for H2PO4 from the table. This is the second constant for phosphoric acid, and it's 6.3 times 10 to the negative 8. So Kb in this case is 1.6 times 10 to the negative 7. Roughly speaking, Ka3 is a millionth, or rather Ka is a million times smaller than Kb, close to a million times smaller. So it seems like a good place to try the approximation of simply taking Kb and solving for the pH with the nice table. In other words, the Ka should be completely neglectable compared to the Kb, and we simply treat this as a 1 molar solution of a weak base with Kb 1.6 times 10 to the negative 7. An ice table for a 1 molar solution of this weak base starts out 1 molar in HPO4. That will decrease by amount x. We'll just treat that as 1 because we will assume x is small, and assume 0 concentration of hydroxide in the conjugate acid of this base, dihydrogen phosphate. Gives x essentially 4 times 10 to the negative 4 for the hydroxide ion concentration. Second protonation we will look at, although may be neglectable, would form phosphoric acid from the dihydrogen phosphate. Kb for that is Kw over Ka for phosphoric acid, 1.4 times 10 to the negative 12, a very small Kb. A second ice calculation gives x is 1.4 times 10 to the negative 12, which would stand for the concentration of phosphoric acid. But clearly, does not contribute markedly or observably to the hydroxide ion concentration, so the hydroxide ion concentration will be treated as 0.004. Alright, so the contribution from the second deprotonation of the second base reaction of a diphosphate is negligible. So this is often the case in which the second Kb is much smaller than the first. See the carbonate example at the beginning of this lecture. That we calculate a pOH of 2.40 for this solution, and the pH then is estimated as 11.60 in this case. This concludes the lecture for Module 7 of Unit 5.